Okay, so I'm talking about some hints for homework set 3, which is due on Thursday, March 4th. And I think problems 1, 2, and 3 are ones that you could already do given what we've already learned about matrix algebra and determinants. But number 4 you can't do yet. I haven't told you about Cramer's rule, and that's the goal of today. Explain Cramer's rule so that you can solve this system of linear equations in terms of x, y, and z. And also this last part, if alpha equals 1, what must beta and delta be in order for there to be an infinite number of solutions to the system of equations? So I'm asking, that's kind of like when it goes wrong, when beta and delta happen to be certain values, you may have this system of 3 linear equations and try to think about, well, what's the solution to these equations? And there won't just be one answer, there will be an infinite number of solutions. Whoops, that's like when the answers break down and somebody asks you to find a solution, what do you tell them? Well, actually, there's infinite solutions. Which one do you want? I can easily give you an equation with an infinite number of solutions. How about x equals x? For which values of x is it true that x equals x? The answer is all real numbers. Every number is equal to itself. So that's what I mean when I say there's infinite number of solutions. It really means it's not specified. I haven't given you enough information to actually specify the value of x. And the equation x equals x is the simplest example of something where it just doesn't tell you anything about x. How can I solve for x when you've really told me nothing about x? So that's what you're going to be looking for at the second part of problem 4. You guys have any questions about the homework? Sorry, there's not a whole lot of time to do it. I posted it, I think yesterday, but just, let me know if you have any questions about it. I can try to help. Let me stop share. Okay, next thing I want to do is more determinants and things like determinants. I want to, did we actually find the determinant of this slideshow, current slide? By the way, here are the properties of determinants. This one right here, det AB equals det A times det B, that's the one you're going to use in your homework when I ask you to solve for determinants and things. I don't think you'll use any of these other ones. Well, maybe you'll use this one. The determinant of the transpose of a matrix is equal to the determinant of the original matrix. That'll be helpful. I don't think you'll use many of these. Oh, maybe this one. I actually forget. But here are some useful properties in case you need them. Let's go on. Did we actually find this last time? Does anyone remember? I think we got to this slide. Didn't. Amina says we did not do it. Do you mind if we do it now?
Looked at it. Yeah, sure. No, I just said we looked at it. We weren't able to start solving it.
Okay. Well, can we do it together? It'll be good review. I'm going to annotate. And I'm going to use just normal black. I'm going to draw. Okay, what is the determinant? Oh, this is, if I asked you to find the determinant, what should be your, I don't know, it doesn't have a name. I usually call my matrices something like A, matrix A. Why? Just so I can be a little more precise here to say determinant of A equals what? Remember how to do this? You can pick any row, but I recommend the first row. These numbers here, 1, 3, and -1. Those are going to be like the coefficients of the determinants of the submatrix that is created by eliminating the row and the column of each of these terms. So the first one would be 1. I'm just writing this 1 here times what? 1 times the determinant of this, oh, I can do undo. So yeah, this submatrix right here. See how I've boxed in this submatrix? I want the determinant of that. I'm going to undo that so it doesn't stay though, but just so you saw it. It would be 0 times 6, which is 0, minus negative 2 times 1. 0 minus negative 2 times 1 is actually 0 plus 2. So that's that first one. 1 times 0 plus 2. Got that? We're done with the 1. Next one, 3. Remember, though, we need to alternate signs. So instead of a positive 3, write a negative 3 here. Now what do I want? I want the determinant of the submatrix created by eliminating the row and column of 3. What do you get? That 4, negative 2, negative 1, 6. I want the determinant of that, which is 4 times 6. I'm going to undo that so everyone okay? I put this t here. I'm about to undo that because I don't want it there permanently. But you can see where it comes from. 4 times 6 plus, sorry, not plus. 4 times 6 minus negative 1 times negative 2. So let's write that. 4 times 6 is 24. And minus negative 1 times negative 2, that's actually 3 negative signs, which is negative. So it's 24 minus 2, I believe. And then the final one we have is plus this negative 1 term. So I'm going to leave it negative. Negative 1 times what? Remember, I'm crossing out these, and I'm left with this. 4 times 1 minus negative 1 times 0. So I'm going to undo. Oops, I want to redo. Nope, undo. And get negative 1 times what? 4 minus 0. Is this what you guys got? Did I do it right? What is this? This is 2. This is 22 times 3 is minus 66. And this is minus 4. Put these all together, you get negative 68. Is that what you got? Negative 68? I mean, maybe you didn't get it. Maybe you just watched along with me. As long as you saw what I did and you agree, yeah, you didn't make any mistakes, that's all right. It's negative 68. I actually remembered that the answer is negative 68 because I saw it a few minutes ago. But do you guys see how I got that? Somebody, oh, you have a comment?
So do you finding them, do you always subtract them, or is that?
What do you mean? When you mean like for, like this is 24 minus 2, that kind of thing? The subtraction in the middle there, or what?
No, like between like each.
Or this one right here?
Yeah, yeah.
Yes, so you should think of this as a plus, then a minus, and then a plus. And it alternates. If for some reason, I'm not going to have you do a 4x4 matrix, but if for some reason you were doing the determinant of a 4x4 matrix, it would still alternate. It would be plus, minus, plus, and then the fourth one would be minus. But so you might say, well, then what's this negative 1 doing here? It's because there was a negative 1 already.
Yeah, all right.
If this negative 1 were here, then it would be minus negative 1. It would actually be a positive 1, but it happened to be there, so that's why it's negative. Does that make sense?
Yeah, thank you.
Sure. So that's how we get negative 68 here. And you might say, what the heck? Who cares what the determinant is? It's kind of useful in a lot of ways. Well, for one thing, it tells you that A is invertible. Remember how we write it sometimes with a negative 1? So we know A inverse exists. I'm actually never going to have you, you know the sign therefore? Therefore, it's like 3 dots. It's the mathematical symbol. I'm not drawing it very well. A determinant of A equals negative 68. Therefore, A inverse exists. That's kind of all we got so far, really, by doing this determinant. What else have we learned about A? Not that much. Oh, by the way, you actually know what the determinant of A inverse would be. It would be negative 1 over 68. Okay? Without even calculating A inverse, I could tell you that's what it would be because of that other property. So let me clear my drawings and I'll have to clear the annotation. So this right here, it says exactly what I was saying before. Only just with these letters here representing the numbers there. But you can always use that. It's always right. In other words, that's me just plugging in these numbers here. The answer is negative 68. That's an example for how to find the determinant of a 3x3 matrix. You can only do it for square matrices. If somebody asks you to find the determinant of a matrix that's not square, you say it doesn't exist. And you're bad for asking me to do it. Or you're being tricky for some reason. Okay. Ready to go on? Let's go on. Oh, sorry, do you have a question? Go ahead.
Yeah, just a quick question. So you said that you can't find the determinants if it's not a square. Does that mean the inverse also doesn't exist if it's not a square matrix?
Exactly. It doesn't even make sense to talk about the inverse of a matrix that isn't square.
Okay, great. Thank you.
Yeah. Let me just clarify a little bit. You should think of the inverse as being like 1 over the matrix in some way, like dividing by the matrix instead of multiplying. You know what I mean? A times B is just that. You're multiplying two matrices. But A times B inverse, it's kind of like A divided by B.
Okay.
So you couldn't do this sort of operation unless it were square. If it weren't square, there's no way you can talk about dividing by, it just doesn't line up.
Okay, yeah, I understand what you're saying. That makes sense.
My shoes are all messed up. Okay, let's go on. Next thing I want to highlight is how matrices are related to linear equations. It's the systems of linear equations. So let's talk about that again. Any system of n linear equations with n unknown variables, let's consider that. And remember, I said this before, this is the only interesting case. If there's fewer equations than variables, then you don't really have enough information to specify the answer. If there's more equations than variables, you get some weird redundancies, which may result in, where there's just no solution. In fact, you sort of expect that to happen where there's no solution. Try to block some of the glare. So the interesting case is when there's n equations, n variables. Here's what I'm going to argue right now to you. I sound like Perd Hapley. You heard with Perd. My name is Professor Lido. I'm about to say the thing that I'm talking about right now. We're watching Parks and Rec. That's why that's in my head. Because we completely went through The Office, all 9 seasons, and now we're on Parks and Rec. It's been a long pandemic, guys. It's been a long pandemic. All right, this system can always be written as a single equation. What do I mean by that? You have a system of equations where, here's one equation, here's another equation, here's another equation. They're all true at the same time. We call that a system of equations. You can write that as one equation. You can write it as AX equals D, where A is an n by n matrix of the coefficients of each equation. X is an n by 1 matrix of the unknown variables, and D is an n by 1 matrix of the constants in each equation. I think before I go on, it's worth seeing this. I just said it. You haven't seen it. And I'm trying to think, what's the best way for me to show you this? The next one. Yeah. Wait, how come that doesn't have, boo, I don't have the animations on that slide like I should. How about just, what's it called? The whiteboard option? You mind if I use that here? Okay. Am I sharing the whiteboard? You can see the whiteboard, right? I want to make this argument to you. If I have an equation like, I'd rather not do X. I'd rather not do black. I think I'm going to make the equation really easy. X plus Y equals 3. That's a linear equation, right? I have another one. 2x minus y equals -1. This is a simple, you guys, can you see what I've written on the whiteboard? This is a simple system of equations, isn't it? If I give you just one of these, x plus y equals 3, that's not enough information to solve for x and y. 2x minus y equals -1, that's not enough by itself to tell you what x and y are. But together, these two equations do tell you what x and y are. You could solve them. I've had you do that in the past. What I want to argue now is that these two equations can simply be written in a different way. And it doesn't change anything. The exact same information is preserved in the matrix way to write it. So let me show you how to do that if you haven't figured it out already. I'm going to take the coefficients here of x and y and say 1 and 1. Those are the coefficients of x, coefficient of y. Then for the next one, I'm going to write it like this: 2 and -1. Okay. And I'm going to say that's a 2 by 2 matrix. Okay, fine. We know about matrices. The next matrix I'm going to give you is 2 by 1. Oh, no. Sorry. Yeah, two rows and one column, 2 by 1. And it's going to be an x in the top and a y in the bottom. Okay. Equals a 2 by 1 matrix, which is 3 at the top, -1 at the bottom. So I'm going to argue right now, tell me if you agree with me, that these two equations written here on the left and this one equation written here on the right are saying exactly the same thing. It's two ways of writing the same thing. So this is, I can be even more clear and more precise here. This equation right here, it's actually a matrix equation. And it's important to remember that two matrices are the same only if every element of the matrix is the same. It's really like saying and. Now, this is a 2 by 1, a 2 by 2 matrix. This is a 2 by 1. Together, it makes a 2 by 1 matrix. It should be equal to this other 2 by 1 matrix. And two matrices are only the same if every element is the same. So when is this equation true? It's when the top element, and remember how matrix multiplication works. It's the first row of this matrix times the first column of this matrix. So it's 1 times x plus 1 times y has to be equal to 3. That condition has to be true. 1 times x plus 1 times y equals 3. Well, that's exactly what's written over here. How about the bottom element? Well, that's the bottom row of this matrix times the column of this matrix. 2 times x times -1, I said times, 2 times x plus -1 times y has to be equal to what's on the bottom of this matrix, which is -1. Well, that's exactly the same information that's written over here. So you should really, really just think of these as being, I'm going to write this equivalent sign, which is like an arrow that points both ways, but usually it's like doubled. This is more math terminology. What's written over here is equivalent, that's what this means, to what's written over here. So what have I done? All right, first of all, any questions about this? Or is it like really obvious? Like, why are you taking 5 minutes to do this? It's obvious. Sorry if it is. No questions? Okay, here's my point. I want to talk about when can we solve, when is it even possible to solve the system of equations? And when is it possible to have a unique solution where there's only one answer? And the answer to that question is perfectly encapsulated in this matrix here, this 1, 1, 2, -1. In particular, it's determined by the determinant of this matrix. So you just learned what the determinant was. Let's call this matrix A. Let's call this matrix, which it is a matrix, although sometimes it's called a vector because it's anytime you have a matrix with either one column or one vector, one column or one row, you could call it a vector, but really a matrix and a vector, same thing. Only that one has that distinction of being one. Okay, this is also a matrix, and usually that's called D. So we can think of this as A times X equals D. This has a solution only if the determinant of A is invertible. It has to be invertible. Why? Because if A is invertible, what can I do? I can pre-multiply. Remember how the difference between multiply and pre-multiply is matters? I'm going to pre-multiply the left side of this equation by A inverse, and I'm going to pre-multiply the right side of the equation by A inverse. And then A inverse times A, that disappears. It just becomes the identity matrix. X is still there. And that times A inverse D. And now the identity matrix times anything just gives you back the thing. So it's just X equals. So this is like the solution to this problem, is that the inverse of A times D is the solution to this system of equations. If A inverse exists, if A inverse doesn't exist, you simply can't do this matrix algebra to get the answer. So what might I expect you to do in this class? Well, one thing is to realize that the determinant of this matrix tells you, that's sort of like, remember in the homework was question 4, second part B. I asked you to find when is there a unique solution? No, not unique. Actually, when is there an infinite number of solutions? So I have to talk about that too, to an equation like this. I'll explain that in just a bit. But for right now, let's think about what's the determinant of A. You guys can calculate that, right? What's the determinant of A? I'm looking at these numbers, diagonal, multiplied minus these numbers, multiplied. What is it? That's the determinant of A. Oh, we're in big trouble if you can't find the determinant of this matrix. It means nothing that I've been saying is making sense. Oh no, I'm worried now.
Is it just 1 times -1 plus 1 times 2?
Close, but no.
Or -1 times 2?
Yes,
Okay.
which is what?
-3.
Correct. Thank you, Kai. Am I saying your name right?
Yeah.
Yes?
Yes.
Cool. I also have seen some of Cobra Kai on Netflix.
I have not.
Okay.
Tell me.
Actually, you know what? I actually don't recommend it unless you're a fan of the original Karate Kid movie. If you're a fan of the original Karate Kid movie, it's like, oh yeah, this is cool. If not, it's
Yeah, I haven't seen it. So.
okay. So when I remember when the original Karate Kid movie came out, and I actually liked it. Daniel-san. We call people Daniel-san a lot. All right. So because the determinant of A equals -3, which is not equal to 0, that means A inverse exists. And that means this system of equations has a unique solution. It has to be unique. How do I know it's unique? Because this is unique, by the way, right? A inverse is always unique. You know what I mean by unique? It means there's not 2 different matrices that could both be A inverse. There's only one A inverse. And you take that A inverse and multiply it by D, that's the answer. Unique solution to this system of equations. Let me just go on because of, preview, because it matters for homework 4, section part B. If determinant A were to be equal to 0, it doesn't mean there's no solution to the equation, to this system. It could mean there's infinite solutions. In fact, it either means there's no solution or there's infinite solutions. And it'll be up to you to figure out which of those it is. And I can try to explain it right now. If one equation is inconsistent with the others, then there's no solution. But if all the equations are consistent with each other, then there's infinite solutions. By the way, what I just said is talking about when determinant A is equal to 0. I should make like a little tree where, like a decision tree. Can I delete what's written here? Anybody want me to save these drawings? I gave you an example of a system of linear equations. I explained how that's equivalent. That's what that red arrow thingy means. It's equivalent to this one matrix equation. Then I said, how do you know if it's possible to solve this equation? It's possible to solve it if the determinant of A is not 0. We calculated the determinant to be -3, which is not 0. Therefore, there is a unique solution. I haven't actually solved it for you.
Wait, what do you mean when you say if one equation is not consistent?
Yeah, I can explain that. But before I do, before I deleted this, I wanted to explain to you and to all future viewers, if there are ever any, what the point of what I wrote on here was. Can I clear it now? And then I'll go to Kai's question.
Yeah.
Okay, I'm clearing it. Now I'm going to, it's a great question, Kai, and I'm going to address that now. What if we had something like this? X plus Y equals 1, and something like 2x plus 2y equals 3. If you let's do it. Okay, let's take the determinant. Let's write it as ax equals d and calculate the determinant of it. I write it as ax plus d. I get 1, 1, 2, 2. Takes a long time actually. Xy equals 1, 3. 1, 3. If I take the determinant of this matrix, I would get det A equals 2 minus 2, which is 0. Uh-oh, we got to the point where because the determinant is not equal, is equal to 0, that means it's not the case that there's a unique solution to this system of equations. We're not done. I'm shaking my finger at you like Dikembe Mutombo. Don't even think you're done. Wow, references from the 80s and 90s. You guys definitely don't get that. If you get to this point where determinant A equals 0, then you have to think, are these equations consistent with each other or aren't they? If they are, then there are infinite solutions because you haven't specified enough. You haven't given me the right information to specify a solution. So there's an infinite number of them. But if they're inconsistent, that means there's no solution. How can I tell which one it is? I would use algebra. Go back to the original, now forget about the matrix ones. Go back to the algebraic ones and try to solve it with like, with equation doings, simplifying. That's the word, to simplify. Just think about doubling this. If you doubled both sides of this equation, equals 1 times 2, right? What would you get? 2x plus 2y equals 2, and 2x plus 2y equals 3. Well, that's impossible. That's inconsistent. Because if you tried to solve that, you could eliminate x, you could eliminate y, you would get 2 equals 3. That's obviously wrong. I would switch to red and do a big bang, right? So if you get to here, det A equals 0, and you're looking back here and saying, well, is it possible to simplify this in such a way that the answers are inconsistent? Yes, that means there's no solution. So there's no solution to that system of equations. How could it have been infinite? Well, so that would have happened. Do you mind if I do some erasing now? I'm going to erase this stuff. Pretend I hadn't done that. I hadn't done that. All I'm going to do is pretend that this 3 is a 2. Maybe you could have predicted that's what I was going to do. So now it's like a different problem now. I'm thinking of, I'm not, by the way, don't just change the, if I give you a problem, don't just change it because it's like easier for you to solve in some other way. I'm not suggesting you do that. I'm saying, what if the problem were different so that this were a 2? Obviously, that would change this number right here. It would have to be a 2, right? How do I write? 2. You would get this far, det A is the same. You would still get 0 here, right? Because there's no, this right-sided equation is nowhere here when you're doing the determinant. You'd still get determinant A equals to 0 because 1 times 2 minus 1 times 2 is 0. Then you would get here and think, okay, is one of the equations inconsistent with the others? I'm saying others because I want you to already be thinking about what if there's more than 2 equations? What if there's 3? What if there's 4 equations? 4 is kind of hard because then you get this 4 by 4 matrix. And I would only ask you to do that if you had a calculator that you could calculate easily what the 4 by 4 determinants were. And I would only do that maybe on a take home, something that was take home, not in class. Okay, where was I? We get to this, once we get here, we get to this question which Kai asked, which is a great question to ask, which is how do you know when there's an infinite number of solutions? How can you test for that? And the answer is manipulate the equations algebraically so that what's on the left-hand side is the same. Somehow you'll be able to do that. It might not be this obvious. I made it really obvious for you that you could just double the top and it would equal the bottom. But you could do that here, double the top. This becomes 2. And you would get to this and simplify it. You would get 2 equals 2, which of course is correct, but it doesn't tell you anything about x and y, does it? We can't solve this for x and y because actually there are infinite solutions for x and y. We could say, here's a little table of x's and y's that solve it. If the x is 0 and y is 1, that's a solution. If x is 1 and y is 0, that's a solution. If x is 2 and y is -1, that's a solution, right? You're very familiar with how this works in math. All of these are solutions to this system of equations. And in fact, anything in between x equals 0 and 1 would correspond. It's like a line. It's like a line on a graph. And you can't say where on the line you are because these 2 equations both represent the same line. Maybe that's the easiest way to put it. If you're somebody who thinks visually, what I'm really talking about now is the fact that this equation and this equation correspond to exactly the same graph. Therefore, there's no more additional information given to me about x and y because it's the same graph. Okay, so operationally, this is how you would answer a question like I asked on the homework, is to think about, okay, first, what's the determinant of A? If the determinant of A is equal to 0, then I have some more exploration to do, which is, are we in the case where there's no solution because the equations are inconsistent, or the case where there's an infinite solutions because they are consistent? And I feel like giving you a lot of help. I don't want you to be confused on the homework, and it's due in 2 days. So I have to stop share, don't I? And share something else. Go back to the homework. Here's the homework. Right? What am I asking you here for number 4? Can you see it? Maybe zooming in helps. Or did I zoom in too much? You can see this for number 4. Here's 3 equations, but remember, you should write that as one equation, one matrix equation, where A equals, and I'm really helping you a lot here. I don't care. I feel like helping you. Isn't that my job? I'm the professor for this class, so shouldn't I just help you? What is someone going to say, hey, you helped them too much, you're bad? No. Oh, that's supposed to be an alpha. That's supposed to be a beta. Z, the coefficient on Z is 1, right? Right? Alpha times X, beta times Y, 1 times Z. So that's the first row of this matrix capital A. I'm thinking about what is the matrix capital A going to look like? How about for this second equation, 2x minus y plus z? That's like 2, it's like 2, negative 1 and 1, right? How about for this third equation? Well, that's like 1. Be careful, there's no y. Don't write 5 here. If you wrote 5 here, you'd be horribly wrong. You'd be permanently banned from this Zoom meeting. You and your children. No, the coefficient here on y is 0, simply because there is no y. And then the coefficient on z is 5. Okay? And then that's like times, I guess I could have just written this in the homework, but I wanted you to get this far on your own. But then I changed my mind and said, you know what, I'm just going to help you. What's on the, oh, here's a good like learning test. Does somebody mind telling me what goes here?
Would it be all zeros?
Close, but no. I get where you're coming from, Jordan. It actually shows you were paying attention earlier, because if you look at the right-hand side of all of these equations, they're all zeros. But there's an important difference between those equations and these. And that is, can you see there are some constant terms on the left side here? So part of what you need to do is take any constant term and move it to the right side of the equation. That's the only way to write it, is ax equals d. Right? Think about it. There's no constant term here on the left side. Everything on the left is either being multiplied by x, y, or z. So if you have something on the left side that's not multiplied by x, y, or z, it has to be moved to the right. So now, given that, can you tell me what belongs here? On the right-hand side of this matrix equation? Can you see?
Sigma 0, 2.
Say it again.
Sigma 0, 2.
Yeah, that's actually a delta, but okay.
Oh, delta. Sorry.
Yeah, it does kind of look like a sigma. Sigma looks like, a lowercase sigma looks like that, right? They look pretty similar. A sigma, a lowercase sigma, and a lowercase delta. I apologize, but I just used the Microsoft Word, I think, for this. But he's right. Delta, then 0, and then 2. So what am I asking you to do here? Use Kramer's rule. I haven't even told you what Kramer's rule is. Oh dang. Am I gonna have time to tell you Kramer's rule? Yes, I'm gonna tell it to you right now. But just for this, if alpha equals 1, like put 1 equals there, what must beta and delta be in order for there to be an infinite number of solutions to the system of equations? You have to think about, when does this equal 0, the determinant of this equal to 0? And then also, when are these equations all consistent with each other? And it could, you have to think about what beta and delta have to be for these equations to all be consistent with each other, okay? So that's your homework. Kramer's rule. Can I go ahead and give you right now an explanation of Kramer's rule? Because it's time. You're all drawings. Share. I want to share my slides with you. Current slide, perhaps. Hopefully, you can see. All right. If I asked you to write this as a system of a single matrix equation, you should be able to do that. Look at the coefficients. They're here. X, Y, and Z are here. And the constant terms, after moving them to the right side, if they're not already to the right side, are 10, 5, and -1. So here's a way to write this equation. I want to show you how to solve it using something called Kramer's rule. And the answer is, I can almost write it for you right now, what the answer is. I can't literally give you the exact numbers, but the answer to this, the solution to this equation is that x star equals the determinant of something called D1 over the determinant of A, where A is the original matrix. We actually already know the determinant of A. We calculated it. It was -6. Oh, no, we didn't. Did we calculate it? So this is a different one. We haven't calculated this one. So, and the same is true for y star equals the determinant of D2. I'm sorry, you can't read this. Forget about that. But that's what it's going to be. It's a preview. What I have to tell you is how to find D1, D2, and D3. For Z star, you're going to have to find D3. But it's actually pretty easy. To find D1, I replace the column that corresponds to the x's with this, with D. So I take that column, those numbers from D, and I put it into there. That's D1. I take the determinant of that 3x3 matrix, and that's the numerator. Then I take the determinant of the original matrix, that's the denominator, and that is the answer. That is what X star is equal to, the solution to this equation. Okay, that's what's known as Cramer's rule. If I want to find Y star, the solution for Y, I have like 13 minutes. I will do, let me undo, how would I do it for Y? I'm going to undo a lot of stuff. I'm going to instead plug these numbers into here. When I say plug, I actually mean replace. I'm going to replace a 4 with a 10. I'm going to replace -1 with a 5. And I'm going to replace a 0 with a -1. I'm going to take the determinant of that matrix, that 3x3 matrix. That will be the numerator of Y. And the denominator will be the same. It'll be the determinant of A. I'm really sorry that these are, so I'm drawing it with a mouse, like squiggling it on using the annotation of the feature of Zoom. But on the next slide, I'll show it to you with real slides. Does that make sense though, as like a preview of what you're going to do for Cramer's rule? It's really just the process of replacing columns of A with D. So for X, you replace the first column with D. For Y, you replace the second column with D. For Z, you replace the third column with D. By D, I mean lowercase d. And then each of those, the first one, D1, second one, D2, third one, D3, those are respectively the numerators of X, Y, and Z. After you take the determinants, they're the numerators. The denominator of X, Y, and Z are all the same, which is determinant of A. Here's an example of this. I'm going to clear my drawings. Go to the next slide. Go to the next slide. So this problem that I gave you before here, 3, 4, 2, 2, 1, those numbers give you a determinant of -92. You can test that yourself if you want to, or just take my word for it. The determinant of that is -92, which, because it's not 0, means there's a unique solution to this system of equations. Great. You could use substitution to find a solution. You've already learned that, but there's a new method called Cramer's rule that I explained. Here we go. Once again, start by writing it as AX equals D. That's the first thing we learned when we talked about this, is how to write it as AX equals D. Then let D sub J be defined as the determinant of the matrix obtained by replacing the jth column of A with D. Oh, by the way, I guess instead of determinant, the D is already the determinant. I think I got this from the book. It doesn't matter whether you have determinant of DJ or whether DJ already is the determinant. Doesn't matter. But that's what Cramer's rule. The unique solution of AX equals D is X sub J. Here's how you should read this, X sub J. It just means the jth element of the vector X. So if your variables, instead of being X, Y, and Z, this is just the generic way of writing a bunch of variables. You should think of this as being like X, Y, and Z, right? X1 is X, X2 is Y, N equals 3, so X3 equals Z. Textbooks do this because they want to be as general as possible and say, well, I don't even know how many variables there are. There could be n, let that be the number of variables. And then we can still talk about Cramer's rule for any size matrix just by calling X this entire matrix or vector from X1 all the way to Xn. And Cramer's rule still works. Only now they're indexed by J. J equals 1, 2, all the way up to N. Guys, have any questions about that? You want to see an example of it? I'm also asking you to do this for your homework on Thursday. Guys, any questions? Let's go on. See an example. All right, so here's our equation, system of equations. Here's the same thing written as a matrix equation. We already found that the determinant of A equals negative 92. If you did that process of 3 times negative 1 times 2 minus 0 times 4 minus 4 times yada, 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 you would get negative 92. But we now need to find D1, D2, and D3. To find D1, I'm going to replace the first column with this column. I do that here. Finding D1. To find D1, we need to replace the first column of A with the only column of D. That's what you get here. 10, 4, negative 2. 5, negative 1, 4. Negative 1, 0, 2. Take the determinant of this, which of course you could do by hand, or you could use a calculator or a determinant calculator online. Those exist. You would get negative 74 for D1. Can I stop here and say, I don't want to go too fast here and say, does everyone see how I got to this negative 74? You think you can do it for your homework? Oh, by the way, for your homework, the determinant won't be a real number, will it? It'll have parameters in it, but that's okay, right? Instead of being an alpha here, instead of being a 10 here, there could be an alpha, but you still calculate the determinant in the same way. And you'll get an answer here, D1 equals something that has to do with alpha or beta or delta. That's okay. It can have parameters in it. But this process of how to get D1, that's what I want you to understand. You guys understand? Mm-hmm.
Yes.
Okay. How about D2? Well, if you understand D1, I'm sure you can do D2. Except now I'm replacing the second column with the 10, 5, and negative 1. I get this. To find the determinant of that, you do a bunch of math and you get negative 244. That's what the determinant of this matrix here is. The homework question, though, you're not going to get an exact number here. You're going to get something that includes the Greek parameters in it. That's okay. D3, once again, I'm going to replace this column of negative 2, 4, and 2 with 10, 5, and negative 1. I get this matrix. It's 3 by 3 matrix. Use some software or do it by hand, and you get negative 139. It's funny how they're all negative. Negative 74, negative 244, negative 139. All right, we're not done because after all, what are we looking for? We're looking for X, Y, and Z. Maybe X star, Y star, Z star, the solution to these equations. Here's how you solve it. Or here's how you just go the final step to actually solve it. X star equals this D1, the determinant of that matrix, D1, over determinant of A. The original matrix is A. You get 0.804. Hey, is that our area code here in Richmond? I don't even know. All of my phones are from Ohio, so I don't even know your guys' area code. Y star, the determinant A is still the denominator, but the numerator now is that D2, which we found is negative 244. There's your answer for Y. Z star, same thing, only with D3 as the numerator, you get 1.511. So we have it, X star equals that, Y star equals that, Z star equals that. This final step here is just a check. You don't have to actually do it unless you want to, just to make sure you got the right answer. You could take any one of these equations, any one of these rows represents a different equation. So let's just take the top equation here. And here's a check to make sure that these answers that we got using Kramer's rule are indeed correct. And that is 3 times x, or 3 times 0.804, plus 4 times y, 4 times that, minus 2 times z, that's that, equals, it should be equal to 10. Well, of course, there's some rounding error when you use a calculator to do this, but it's pretty good confirmation that yes, it is correct. And this process, I guess, is a mathematician named Kramer who calculated it, came up with it, and it's just called Kramer's rule. And it is not the only way to solve a system of linear equations. It's just one I thought I would like to teach you. I had the option of whether to teach it to you or not. And I actually don't think it's like really, really important to learn this. It's actually just good practice of working with matrices, working with determinants. And I don't know, it's kind of a nice little way to package this information. So you guys have any questions about that? For the last few minutes, let me show you a little bit of an equation where there are parameters in it. Because remember, your homework problem has parameters. I've said that many times. You guys are probably sick of me saying that. What if you get something like this? Oh, wow, that looks crazy, doesn't it? Alpha x plus beta y equals, this is actually a gamma. 1 minus alpha x plus 4 beta y equals delta. What if you see something like this? Can you use Kramer's rule to solve this? The answer, of course, is yes. Math doesn't care if you're working with numbers or parameters. It treats them the same. So use Kramer's rule to solve this. What would you do? First, write it. Here's the answer. You first write it as a matrix equation. If you want to just confirm that this is correct, look back here. Alpha x plus beta y equals gamma. That's what you would get here in this first row. Alpha times x plus beta times y equals gamma. 1 minus alpha times x plus 4 beta times y equals delta. Is that the same? Yes, it's the same. So here's a way to write that system as a matrix. Now let's think about the unique solution. Is there a unique solution? Well, yeah, there is. Oh, sorry. There is if the determinant is not equal to 0. Well, here's the determinant. It's alpha times 4 beta. That's this. Minus beta times 1 minus alpha. That's this. That should not be equal to 0, which is there. Let me simplify this a little bit, and you get 5 alpha minus 1 times beta should not be equal to 0. When is that true? When is 5 alpha minus 1 times beta not equal to 0? It's a nice property of numbers that when you're multiplying them, they're equal to 0 if at least one of them are equal to 0. So to take this not equal to 0, that's equivalent to saying both of these terms are not equal to 0. 5 alpha minus 1 is not 0, and beta is not 0. And that's what I've written here. Alpha has to not be equal to 1/5, and beta has to not be equal to 0. Actually, I think that's what I was asking. Under what conditions does the following system of equations have a unique solution? Under what conditions does the following system of equations have a unique solution? The answer is alpha has to not be equal to 1/5, and beta has to not be equal to 0. You guys get how I got that? I know the class is like running out of time now. I get 1:45 as my time on my phone. But do you see how I got here? This maybe this was the most difficult of all the problems I did today. I'm not sure. But here's a question. The answer is alpha equals not equal to 1/5 and beta not equal to 0. And how did I get that? How did I arrive at that answer? I used this fact that once you write it as a matrix, you can take the determinant of that coefficient matrix and it should not be equal to 0. And that's the answer. You see that? I don't think I actually went all the way to use Kramer's rule to solve this, but that's okay. You couldn't you? Maybe I'll leave that as an exercise to you if you want. Although if I were you, I would work on the homework. If you want more practice, then do this. use Cramer's rule and you can actually solve for X and Y. It'll be in terms of alpha, beta, gamma, and delta. All 4 of those parameters will be part of your answer for X and part of your answer for Y, I believe. All right. You guys have any questions? I think I'm over my time now.